students, this video is going to go over the half-life of these isotopes. So when we're talking about radioactive isotopes, we've talked about how they are unstable and that they are going to decay, and they're going to undergo some kind of nuclear decay and give off some kind of radiation. And so when we talk about how often they decay, it does vary depending on what specific element or isotope rather that we're talking about, because each isotope, even of the same element, is going to have a different half-life. So the half-life is talking about the time it takes for a sample to decay by half. So let's say that we have 10 grams of a sample. How long does it take for that sample to get down to 5 grams? However long it takes for that to happen is the half-life. And so after each half-life, the sample decays by half. So when we're talking about comparing, the different half-lives of these different isotopes, substances that have a very short half-life are very unstable, and those substances that have long half-lives are more stable than those that have short half-lives. So in comparison, we have fluorine 20, fluorine that has a mass number of 20, it has a really, really short half-life, only 11 seconds. So that particular sample is very unstable. Whereas we can talk about uranium-238, and that has a half-life of 4,700,000,000 years. So it would take that long, 4,700,000,000 years, in order for a sample of uranium to decay by half. That has a relatively really long half-life, and so that substance would be more stable than that fluorine 20 that only has a half-life of 11 seconds. So half-lives for different substances can be conveyed in seconds. It could be conveyed in days, years, so on and so forth. So this is a graphic example of half-life. This is telling us that at a time of 0, we have 100 grams of a sample. And as you can see, after each half-lives on the x-axis here, our sample decays by half. So we start with 100, and then we go down to 50, and then we have 25, and then we have 12.5, and then we have 6.25. So we decrease our sample by half every half-life. And you can see that the time is in years. This is 12.3 years. We double this time, 24.6 years. We add 12.3. 36.9 years, so on and so forth. So each half-life adds 12.3 years to that to this graph. A different kind of curve here, this is talking about iodine-131. On our axes, this is telling us how much we have remaining, and this is telling us how many days. So our days here are going to represent our half-life. Each dot represents a half-life. And so our sample is 100 to start with, 100%, and we go down by 50. Half-life decreases by half. You can see that that is 8 days. 50 decreases in half to 25, decreases in half to 12.5. So each half-life covers the same amount of days, but we are decreasing our sample by half each and every time. So we can do some calculations here with our half-life. So let me get my little tool ready here. And we have a sample of radon-222 that decays with a half-life of 3.82 days. So after every 3.82 days, we decrease our sample by half. So it says that if an initial sample of the element contains 1,000 atoms, how long will it take for the sample to decay down to 125? So we are starting with 1,000. So what I'm going to do is see how many half-lives pass. So after the first half-life, I'm going to decrease by half, so that's going to be 500. That's going to decrease by half to 250. That's going to decrease by half to 125. So 4 half-lives have passed because it has decreased in half that many times. Now let's see how many days have passed. So we start at 0 days because at 0 days, we had 1,000 atoms. So each time we're going to add 3.82 days. So this is going to be 3.82. And so then I'm going to add 3.82 to this, and that would be 7.64 days. And then I'm going to add 3.82 days to that, and I'm going to get 11.46. So each half-life is represented by 3.82 days, which is why I've added 3.82 days every time I had a half-life. Okay, so that's how I do that. Maybe this should have just been 3 half-lives because ground zero. So let's take a look at this next one. An initial sample of zinc 61 contains 215 grams. After 976 days, the sample size has reduced to 13.4375 grams. So what is the half-life of zinc 61? So we're trying to figure out what the half-life is. So we are starting with 215 grams. So here's what I want to do. I got to figure out how many half-lives have passed. So my sample has to decrease by half. So I'm going to divide that by 2. That gives me 107.5. Then I'm going to divide it by 2. That gets me 53.75. Because remember, each half-life decreases my sample in half. Now I've got 26.875. I'm going to divide it by 2 again, and I get 13.4375. So I have divided by 2 each of these times, divided by 2, because each half-life I have decreased my sample by half. So now I got to figure out how much time has passed. My initial time frame was 0 at 0 days. I started with 215 grams. After 976 days, this is how much I have left. So I have had 1, 2, 3, 4 half-lives. So I'm going to divide my total time, which is 976 days, divided by my number of half-lives, divided by 4. And so I've got 244 days. And I can check my work because I should be able to add 244 here each time and get up to 976 to check my work. It's 732. If I add 244 to that, I do get 976. Okay. And then let's take a look at the last question. So it says thorium-230 decays with a half-life of 80,000 years. If an initial sample has 10 grams, how much will remain after 240,000 years? So I have, and my initial time is 0. Every half-life, so 1, 2, 3. Every half-life is 80,000. So I'm going to add 80,000 each time to this so I can see how many half-lives have passed. And I have just 3 half-lives. So in order to see how much is left after 240,000 years, I'm going to decay my sample in half until I get to this box right here. So I'm going to divide it by 2. That's 5 grams. I'm going to divide it by 2. I get 2.5 grams. I'm going to divide it by 2 and I get 1.25 grams. And that's how much I have left. So if you have any questions while you're working through the half-life problems, don't hesitate to ask. All right.